Yeah, good morning. I'm happy to be here talking about and giving you some insight on nutrition and movement. And I probably mainly will focus on the bone and bone metabolism. And when we look on the development of bone mass during aging, we'll see that we build up, both men and women, a so-called peak bone mass until the age of about 30, but that depends very much on the physical activity. So if we do have a couch potato sitting in front of the computer all day, the peak bone mass will be much lower than for somebody who's really very physically very active, doing a lot of exercise. So those who are more couch potatoes will start from a lower peak bone mass and then will decrease bone mineral density with age. So they are in a less good shape as those who are doing very much physical activity. Now, there are several factors causing bone loss over time in men, which we can see here and which was nicely reviewed by Banu. So these are the age-related osteoporosis on where the hormones play a role, or some medication can play a role. But what I think the main part which we can see is the decrease in physical, or the lack of decline in physical activity. So independent of what the reason for the physical inactivity is, I think that's one of the main causes which lead to bone mineral loss in bone density over lifetime. This is supported by the so-called mechanostat hypothesis, which has been developed by Harold Frost. And he was saying that the mechanical usage is the main predictor for bone mass. So the bone, which you build up with your peak bone mass, will need a minimum effective strain mechanism in order to keep up that bone mass. So all of you will have a turnover, so meaning the bone formation cells, the osteoclasts, will build up bone, and the bone resorption cells, the osteoclasts, will just degrade bone. But in a balance, you keep up your bone mass in case you keep the minimum effective strain mechanism. Then it leads to modeling or remodeling. But even in the case if you are 40 to 50 and you think, well, now I'm like to turn from a couch potato to heavy exerciser, then the osteoblasts will turn on and you will build up bone mass. So there is the modeling process. And there is a so-called mechanostat which just makes that relation between the modeling and remodeling process and bone. Now, that threshold of minimum effective strain can be affected by several other parameters, and one of those is nutrition. So nutrient intake may affect the threshold of the minimum effective strain, so meaning a malnutrition may lead to less bone mass, even though you might have a heavy exercise. Now, usually the bone mass and bone mineral density is measured by DEXA, so dual energy X-ray absorption, or quantitative computer tomography. These are measures which give you a nice idea what the bone mass is, but they don't give you the idea of bone turnover. And it takes much longer to see any change in bone mineral density with those methods like DEXA and QCT than with those so-called biomarkers, and this is reflected in this comic here. So these are reflecting the osteoclasts, and these are reflecting the osteoblasts, the bone forming cells. So now, while the bone is formed, there are biomarkers let into in blood. For example, the procollagen 1 type propeptide, CP1P, or sometimes it's also P1CP, or the bone alkaline phosphatase. And on the other hand, the bone resorbing cells, they degrade bone, and you see from the degradation just metabolites of collagen in serum and urine. This is, for example, deoxypyridinoline or N-telopeptide and C-telopeptide, and they give you an idea of the bone turnover and the activity of bone turnover, even in a short period of time. So when you look at these bone turnover markers in aging, and this is a nice study or meta-analysis which was done by Schultz, you see here the bone formation markers in men and women over lifetime. So this is the concentration of bone formation markers, and you see with age there is a decrease in bone formation markers in men, while in women they are almost stable until menopause, and then they increase. So there's an increased bone formation, concentration of bone formation markers, so an increased activity of osteoblasts in women. Looking at the bone resorption markers, you see in men that there is an increase with aging, so a decrease in the bone formation and an increase in the bone resorption markers. And you see again after menopause in women also that increase in bone resorption markers, and in balance there is the increase in bone resorption markers in postmenopausal women is much higher than the bone formation, so that's the reason why there is a decrease in bone mineral density. Now, as I said, I think mostly, or the significant cause for the loss in aging, loss of bone in aging, is from my point of view immobility. And there are other things, other causes which lead to immobility. As you heard, I'm involved in experiments in spaceflight. So in spaceflight, the astronauts are not really inactive, but there is a lower mechanical loading of the lower part of the body because of the loss of the G factor. And that also holds true in bed rest, and this is also from these space research studies. So we use bed rest, and in this case a 6-degree head down tilt bed rest, as an analog model to mimic some aspects of spaceflight. And one aspect is the change in bone turnover. Although the increase in bone resorption markers in bed rest is not as high in bed rest as in spaceflight, this is really a very nice model to study it. And again, in aging, I think over time there's a significant effect on physical inactivity in aging on bone mass and bone mineral density. Now, when we look at the results from spaceflight, and you can imagine that we see some malnutrition over the years and decades of spaceflight in astronauts, since they are free to choose whatever they like to eat. And we tried to educate them in the past years to have an eukcaloric nutrition, to have enough energy intake, since they lack energy intake and food intake because they have a decrease in smell and taste sensations as well. Probably it's a different mechanism, but still they do have, and because of that they don't like to eat as much as they should. But they are more aware of it, and so they are starting to have a better food intake. Now, in addition to that, you can imagine that physical activity is really something which is a main countermeasure during spaceflight. And NASA developed what they called an interim resistive exercise device. This was launched in 2002, but it turned out that the force which could be developed with that device was not enough to keep up the mechanical load. And so in 2000, I think it was 2009, the advanced resistive exercise device was launched, where they had where they could build up a higher force. Results from these experiments show that as you can see, the energy intake here, and we distinguished in our study between astronauts who took part in space studies on the Mir station, which was a Russian space station, which was destroyed in 2000. And those astronauts who participated in resistive exercise on the IRAD and others on the ARAD, and you see those on the ARAD had a much higher energy intake, and also their vitamin D level, which affects bone turnover for sure, because it leads to mineralization of bone and calcium uptake, was better in those ARAD astronauts. Now, when they have that more adequate nutrition, what you see is that bone mineral density can be kept independent of sex. So you see here the percent change of bone mineral density per month And you see those who had that lower exercise and inadequate nutrition had a much higher decrease in bone mineral density than those who had the IRED. So combining an optimal nutrition plus a resistive exercise seems to be one optimal countermeasure in microgravity. And this is also supported by the biomarkers of bone turnover. You see here the bone resorption marker N-telopeptide, and here the bone formation marker bone alkaline phosphatase. There seems to be no big difference in the bone resorption marker, but you see at the end of the mission for sure there's an increase in bone formation marker. So that reflects very much that combination seems to work. And that was the first time that we could keep up almost bone mineral density in these astronauts. Now, as Bill just referred to, high protein intake is one measure to increase muscle protein synthesis in the elderly. Now, if you put even healthy young people in bed, you also see in an eucaloric diet a decrease in muscle protein synthesis. So that effect is similar in aging as in young healthy people put in bed. Showing, from my point of view, showing again that physical activity seems to play a really significant role in that development. On the other hand, high protein intake also improves glucose tolerance. And again, if you put healthy people in bed, you can induce a glucose intolerance in 5 days in bed. So these developments are very parallel to what happens in aging. So what happens, and there was one question today from the audience, if you increase protein intake to the bone? So I think it's not just protein intake. I think it's the acidity of the diet which results from an increase in protein intake. And when we look at the food high in protein, we come to milk products as well as meat and fish. And if we look at the products which are more alkaline, we see fruit and vegetables. So I think it's rather the relation between the acidity delivering products compared to the baseline, the base precursors like fruit and vegetables. In other words, if you have your fruit and vegetables with your steak, that might be less tremendous to bone than just having the steak without any fruit and vegetables. So what you can do is you can really calculate, according to an equation developed by Rehmer, the potential renal acid load of a diet, which is called PRAL. And what is taken into account here is the protein of the diet you are consuming, the phosphorus, the potassium, the magnesium, and the calcium content of the diet. So all of those nutrients play a role in the acidity of the diet. And if you then get a negative potential renal acid load, that means it's more alkaline. And if you get a positive potential renal acid load, this means it's more acidic. So a more acidic diet seems to be not as good as a more alkaline diet. Because in the aging, with a more acidic diet, you are getting more protons. Now, proton excretion in the elderly is less pronounced as in the younger people. So it's one part, it's the acidity of the diet. On the other hand, is to excrete the protons from the blood into through the kidney. Now I was able to participate in a study. It was a cross-sectional study which was called Concord Healthy Aging in Men Project at the University of Sydney. And what we did, we analyzed the potential renal acid load of their diet in a way that we asked for their food habits in 1 week. Meaning we asked what they prefer to eat in 1 week when they were at the age of more than 75. So all these men were older than 75, and there were 920 men. So we analyzed the food habits based on the fact that food habits don't change that much over lifetime. So you really have to be very active and to change your food habits. So the basis was, obviously, if we ask for the food habits today, they probably have had those food habits for the past 70 or more years. When we did that, and here you are seeing the bars, the light blue bar shows the positive prior, meaning a more acidic diet, and those who had a negative prior, a more alkaline diet. You see that the bone mineral content is higher in those who had a negative prior, and for the bone mineral density in the different areas, you see, you see that those who have a negative prior, meaning a more alkaline diet, their bone mineral density is less decreased. So there seems to be a relationship, and it seems really that there is a positive effect of negative prior, meaning a more alkaline diet. Now getting back to the bone turnover in bed rest and our model. Now what we see in bed rest, and this is a 17-week bed rest study, and this is the bone resorption marker and the bone formation marker, you see that in bed rest there is a significant increase in the bone resorption marker, and if you apply resistive exercise, that decreases. So that's similar to what we saw in spaceflight, and that's probably very similar to what we see in aging. And you see again that with resistive exercise there's an increase in the bone formation markers. Now you can see that even in very short-term bed rest studies. So when you put young people, and these were 10 young men in a crossover design study in a metabolic ward, they had the identical diet in both periods, individually tailored, and what you see is, this is the 4-day pre-phase adaptation period, and then you see here's the bed rest period, that on the second day of bed rest, under these very standardized conditions, there's a significant increase in bone resorption markers with bed rest. There's a trend of decrease in bone formation markers, but not getting significant in that very short period of time of 6 days of bed rest. Similar results we see in sclerostin, which is a glycoprotein synthesized by the osteocytes, and that increases and leads to an activation of the bone resorption markers, the bone resorbing cells. So that's similar to what happens in aging. Now what happens if we increase dietary protein intake in bed rest? Now this is a study which has been performed in Toulouse. It's a bed rest study in women, a parallel group design, 8 women per group. And what we did, the control group received 1 gram of protein per kilogram body mass per day, while the intervention group received 1.6 grams of protein per kilogram body mass per day, and that was given isocalorically, meaning they got a lower fat and carbohydrate intake. When we look at the bone formation markers in these groups, we see there is no real significant effect in bone formation. But when we apply that high intake of protein, there is a significant increase in the bone resorption markers over 60 days of bed rest. And that happens quite early, meaning the first urine samples we took was 14 days in bed rest. So, and then the bone resorption markers were really very high. This is also underlined, that's the same study. The total density, bone mineral density from baseline was not different between the groups. But if we look at the cortical thickness, there is a significant decrease in cortical thickness, and if you look at these 2 values in head-down tilt bed rest, day 15 and 43, in the high protein intake group. So there seems to be, even in a rather short term for measuring cortical thickness, seems to be, the effect seems to be reflected in cortical thickness. Now, as I said, since high protein intake seems to have a positive effect on muscle protein synthesis and glucose tolerance, this could be a very well countermeasure for bed rest, but we could also think of how can we improve the diet for the elderly. Now, what we did in another study, and this was in men, we applied potassium bicarbonate. As you've seen in the CHAMP study, there was a positive effect of an alkaline diet on bone mineral density. So if the alkaline diet is really the cause for the effect on bone and bone markers, the application of potassium bicarbonate as a supplement would support that hypothesis. And that's what we really found. This was a crossover design study, only 21 days of bed rest. These are 2 bone resorption markers. These are the adaptation periods here. And you see in bed rest, there is no difference with high protein intake. The control had only high protein intake. In this case, it was 1.8 grams even per kilogram body mass per day. And the supplementation was by 0.6 grams of whey protein because that has a much better effect on glucose tolerance. But you see, obviously, that application of potassium bicarbonate was able to counteract that further increase in bone resorption markers, underlining that acidity of the diet seems to play a significant role in the development or in the change in bone turnover markers and change in bone mineral density. So in summary, what we have seen is that immobility or aging, and maybe the immobility part of aging, leads to a decrease in bone mineral density. When we would add the amino acid or protein supplementation, that seems to lead to a low-grade metabolic acidosis because of the acidity of the diet. And that will further increase the bone resorption markers, since the bone resorption markers need a certain acidity in order to get activated. Now, when applying an alkaline diet or supplementing with potassium bicarbonate, that increase seems to be compensated. So I think that's quite an interesting and good recommendation for aging to just increase the precursors, the alkaline precursors in the diet. So and in conclusion, what I think, I know I'm biased, but I think that regarding bone turnover, the observed effects in bed rest are very comparable to those in aging, and I think that's a nice model to try to understand for bone turnover some aspects of aging. And with that, I'd like to thank you for your attention.